Okay, let's look at our first example, which is the renewal chain. We've seen a specific instance of one, and here I'm considering a more general setup where the transitions from 0 to x are arbitrary probabilities qx. And these are, of course, non-negative, and they must form a distribution. Right? For this to be a transition probability, meaning that you must go somewhere from state 0, the sum over the qx has to be 1. So q is a distribution. And then, of course, the transitions from any state x plus 1 down, right, decrementing by 1 unit, always happens with probability 1. So regardless what number the chain is in, it always goes back to 0 deterministically. And the state space is all natural numbers, so it goes out to n and then past that. So if you remember the canonical example, this was sort of the model of the lifetime of a light bulb, where if you transition from 0 to some qn is this a lifetime of this light bulb, and after n days, right, the number of steps to back to 0, the light bulb goes out, and the guy has to go to the store and buy another light bulb, and then the process repeats. So it shouldn't be too mysterious that this process is not reversible. Specifically, the intuition we're kind of building on here is that if you watch this process, you can tell the direction in which time is moving. Specifically, when this video of this process is being played forward, that we'll see a countdown from n to n minus 1, n minus 2, and all the way down to 0 until this light bulb kind of goes out. And note that's very different than watching this movie played backwards, where there's this inching forward from 0 to 1 to 2 to 3 until finally we get swept back all the way to 0. Right? It's the same difference as watching the guy go to the store and take the light bulb back home, or bring the light bulb to the store and then come back without one. Right? So it's very different, and so all our intuition points to the fact that this is not a reversible process in general. But that does not mean there aren't specific instances where I can manufacture, right? I can bake these cues perhaps in such a way that you do get reversibility. And the example that I could think of is right here. So let's, first thing you want to do is try to maybe use this intuition about the video playing forward or backwards. And here, look at what's happening, right? This process is going to maybe circle at 0, right? Stay at 0, then go to 1. Then from 1, it goes back to 0. Then it circles in 0 again. Then it goes back to 1. Then 0, then stays at 0 for some time, then goes to 1. Regardless of whether this video is being played forward or backwards, it looks the same. We stay for some amount at 0, we go to 1, immediately transition to 0, stay some amount of time at 0, go to 1, back again, right? And regardless of how you play the video, it just won't matter. So we, hopefully I've convinced you that there's a clear possibility that this example will satisfy reversibility. But if we want to show this rigorously, right, a mathematical proof, right, so to speak, then you need the stationary distribution, and then you need to show that it satisfies local balance relations for all pairs of states. So at least in this example, it seems to me that it's fairly easy to work out the stationary distribution. I've done so right here. What I've taken is like my usual suggestion. I've started with a stationary measure, and since I already assume that this is reducible, I just start with my local balance condition. I take a pair of states. I took here 0 and 1. I get mu0 for free, so I set this equal to 1. Q1 is my probability of going from 0 to the other pair, to the other state, 1, right? That's what Q1 is, probability of going from 0 to 1. And then I'm multiplying this by 1, because here, to fulfill local balance, I also need a transition from 1 to 0, right? The pair of states, the flow between these two pairs of states should match. And so you have to put a Q1 here, representing this arrow, and you have to put a times 1, which I've omitted for obvious reasons, because of this transition here. And so immediately I get the solution that mu1 is equal to q1, and then right away I get my stationary distribution. So now let's check if it satisfies detailed balance, and we should do this for all states, but for now I'm focusing, perhaps for obvious reasons, on state 0 and 1. So what are the ways to go from 0 to 1, or what is the probability with which we go? And it looks like I already have my first mistake here. This is supposed to be 1, and this is supposed to be 0. Right, so you can check me on this, but the idea would be that pi of 0 is equal to mu 0 over the sum, and mu 0 was 1, and so this is my mu 0, and this is my mu 1, and otherwise it wouldn't have worked. So now I'm going to check detailed balance again. I'm going to start at state 0. The probability of going to state 1 is q1. When I multiply this by q1, I get pi 1, and I need to multiply this by the probability of going from 1 to 0, and that's precisely the same thing, and so I get local balance verified for states 0 and 1. These two sum to 1, and as sort of as we intended, pi 2, pi 3, any pi x for x greater than or equal to 2 is equal to 0. And so you should, clearly, argue, in addition to what I've just argued here, that local balance is met for all pairs of states. And since 0 is always equal to 0, you can very easily verify that. Perhaps, any pair sort of out here, right, where everything is just completely 0 is completely trivial. Maybe the only other case that's not entirely trivial is, say, the state 1 and a neighborhood state 2. Here, because the transition from 1 to 2 is 0, you will match the right-hand side, which is going to be pi 2, which is 0. So, there's maybe quite a bit more to write here, but it's all fairly trivial. So the only other thing you may want to press me on is whether this is the only such example. And maybe you could also try to see, can I break this somehow by setting q1 equal to 0 and q0 equal to 1? That won't work. It's still reversible, but things look a little bit different. If I set q0 equal to 1, then the chain will just stay in 0 forever, and that's also a reversible chain. You can verify that exactly by the same argument as I've done here. And notice that nothing in these numbers required me to put any condition on q1, right? q1 could be 0, and this all would still work. So the only last kind of thing that you could press me on is whether this is the only such example. Could you maybe come up with something else? And I think you can try to argue that's not the case, and just sketch out the argument. Any example besides this would have to add an additional state, right? So some additional state, let's say n, right, n greater than 2 would have to be added. And then once you add this, you can immediately show that local balance cannot possibly hold because you cannot transition this way, right? You cannot in one step transition over to those states. And so if you like, you can kind of try to practice writing down a convincing and logically sound argument, but the intuition for that is fairly clear, right? Adding any other example would clearly violate local balance with respect to, say, state 1 and that state that I'm adding into this diagram to create my supposed example of a reversible process, which it is not. So I'll leave it there. I think this is, in your homework you have something similar, so perhaps you could try to come up with a maybe slightly more rigorous argument that I've done here, or at least write out sort of the sketch of one as I've discussed.